unit step function. Again, this is going to be used to replace the switch. Having that switch open, close, we're going to write it mathematically instead of drawing it there. So let's see, what is the unit step function? Let me just get a ruler here, make it look a little bit nice. Well, actually, it doesn't really matter. It's called u sub t. The function u sub t is defined like this, graphically. This is u sub t versus t. It has a value of 0 for t less than 0. Then once t hits 0, it jumps to 1. That's a unit step function. So you can write that u sub t as zero for t less than 0 and 1 for t what? Greater than 0. Notice as 0, I didn't even mention 0 there because we really have no value. That's in the process of going from 0 to 1. So what is it? Is it 0? Is it 1? So that's why that spot here, we leave it out. Now, a lot of times the function does not start at 0. It might start somewhat later there. So you might have a function called u sub t minus t0. And that will look something like this. It has a value of 0 till you hit t0. Then it jumps to 1 when you hit t0. So this one, again, it has a value of 0 for t less than t0, has a value of 1 for t greater than t0. Let me continue with that. What does 5 u sub t look like? Yep. It has a value of 0 up to here, then it jumps to where? To 5. So 5 u sub t, it has what? A value of 0 for t less than 0. It has a value of 5 for t greater than 0. You'll see why I'm using numbers like these. What about negative 3 u sub t minus 2? What does t minus 2 look like? Just t minus 2. 0 up to 2 seconds, then 2, right? Well, it's going to be the same thing. When you take a 0 multiplied by negative 3, what are you going to have? 0. This is the 2 second. So if I didn't have the 3 here, it will be 0 up to 2 seconds, then it goes to 1. Well, having the minus 3 in the front is going to make it what? What's 1 times a negative 3? Negative 3. So this, what's negative 3 u sub t minus 2 is going to have a value of 0 for t less than 2. Is going to have a value of negative 3 for t greater than 2. So what's the hoopla about this unit step function? Why we care about it? Let's take this circuit. Let's say I have this circuit, 5 volts, and I'm going to close it at t equals to 0, R and L.
This time it's closing at T0.
Yep. That's closing. So for t less than 0, how much current going through the circuit? None. What's the effect of this source? None. It's not even being there. And what happens when t equals to 0? This becomes what? 5 volts and it's part of the circuit. So for t less than 0, this is not even a factor. So isn't that equivalent to having a source that looks like this? And the source now is 5 u sub t. When t is less than 0, this is 0, 5 times 0 is 0. That's the same thing as this, has no factor. When t is greater than 0, this is 5, and what's this one? 5. So instead of drawing these switches there, you're going to see us probably use unit step function. That's why we're interested in that. What happens if your source looks like this? If you have a circuit, and you go, this is Vs. This is R here, and this is Vs. And Vs, I draw Vs for you that looks like this. I don't know. Let's say it's 4 here, and this is like 1 and 3 maybe, second. Let's say we have something like this. What is that? You can take that source that you see here, that step there, and rewrite that using unit step function. Look at that source. And what about if I take this source, this goes to 4, and let me add to it this source. What would you have if you take this and add to it that? Let's look at for t less than 0. What's 0 plus 0? 0, right? Between 0 and 1, what's 0 plus 0? Still 0. That's the 1. This is the 3. Between 1 and 3, what's 4 plus 0? It goes to 4, right? And what happens after the 3? What's 4 plus a negative 4? Back to 0. You end up with that source. So that source is the sum of this plus this. So I can write that as what? It is actually 4 times what? U sub t minus 1, subtract from it, or add to it the opposite, 4 u sub what? T minus 2. You adding these two. This one is a negative 4 u sub t minus 2. This is 4 u sub t minus 1. And you adding them. You adding this to that to get this one.
Oh, did you mean minus 3 for that second source?
Oh yeah, 3, thank you. That's a 3 here. Yeah. So I can replace that source now with these two sources. Instead of drawing that switch there, I go, you know what, that Vs here, let's put these two functions. So that circuit now, I can rewrite that as and it's 4 u sub t minus 1. This is negative 4 u sub t minus 3. Or if I don't want to put the minus, I can flip this, put the minus on the top, the plus on the bottom, make that a 4 here. So, or 4 u sub t minus 1, as I said, and flip the second one. And I can go like this, 4 u sub t minus 3. And if I want to use superposition, find the effect of each source and solve it, and combine them at the end, I could. Remember superposition, when you have two sources, you look at each source separate, at the end you add them together, and you see what your answer is. Okay, now all the problems that we did, every problem we did, it happens to fit this equation. That number was a 0. What happens if that number is not a 0? Then we have another constant. So let's look at that. Your circuit, after you flip the switch, is no longer a source-free circuit. Before, it was a source-free circuit. There's no sources left in it. That's why that value was 0. What happens after the switch if there's a source in it? Meaning, you have a circuit that looks like this.
Those the notes that you just filled in?
Yep.
Alright, you just have to take a picture.
Yep, I didn't take a picture yet. So let me take this circuit, and instead of drawing switches here, I'm going to use unit step function. Twelve u sub t minus 3. One K, 5 millihenry. Or 50.
I know this is, I'm just curious, does it really matter which way that the inductor is drawn?
No.
So like if like the squiggles go that
One side,
way?
no.
Okay,
No.
it doesn't matter. Just curious.
Yep. Left-handed versus right-handed? No. Whoever wants to draw them.
Yeah. I was just
Yeah.
curious if there was any
No.
significance in that.
Now, when you look at that circuit, just like before, if you look at the circuit for t less than 3, because this one does not kick in till t equals 3 seconds, right? So when you look at that 12 u sub t, this is what you see. T less than 3. What's the source there? Nothing. You have no source on the circuit. So your circuit looks like this. Let's say this is the current. What is I sub L is 0 minus? 0. There's no source in it. What is I sub L is 0 plus? Also 0. Now what about for t greater than 0? I mean greater than 3. The source is going to come in, that's 12 volts. Notice I changed the direction, Joe. Now I'm going to write an equation for that. Negative 12 plus 1K I sub L plus the voltage V equals L, which is 50 millihenry. The derivative of that take the minus 12 to that side, becomes 12 divided by 50 millihenry in one shot. Let's see what we have. I'll try to do them in one shot. 1K over 50 millihenry, what's that number? 1K divided by 50 millihenry. Looks like 20,000. Equals 12 divided by 50 millihenry. $240. Notice this number is no longer 0. This is the first time so far you've seen that number there. So we have an equation that says if you have a differential equation that looks like this, equals A, not a 0 now, then your solution is going to be A over alpha plus K e to the minus alpha t. Right? That's the handout I gave you.
The handout, but the handout has dx over dt, not dx to the t over dt, which I don't think
What?
is really a big deal. The kind here just says dx over dt.
Yeah?
There's up there, there's a t next to the dx.
Oh, as a function of time, yeah. Yeah.
I don't think that was a big deal.
Yeah. So this is my alpha, and this is my A. Ready, guys, there? So I sub L as a function of time is going to be A over alpha, 240 divided by 20,000 plus K e to the minus 20,000 t for t greater than 0. Ah, 3, thank you. Keep forgetting this is for 3. Dave, you guys there paying attention or doing something else? 240 divided by 20,000. Oh, 240 divided by 20,000. 0.012. Or 12 milli if you want to. plus k e to the negative 20,000 t. Now we need to find k. It's not as easy as it used to be. Well, it's not that difficult, but it's a little bit, mathematically, a little bit more than the previous one. How do we find k? This actually, I should say 3, not a 0 here. Remember, for t less than 3, right? Three, not 0. We know the current at 3 minus. We know the current 3 plus, because that switch opens at 3 or swings at 3. It's 0. So here we go. I sub L at 3 plus is equal to 0. I should be able to solve for k now from that. I sub L at 3 plus, let me say 3 plus, that means really 3.012 plus k e to the power of negative 20,000 times 3. Was that a milli? Just curious there. What is that problem? Nope, just 3. So you plug that number in and you solve for k. Oop. We know what the answer is equal to. That's a 0. So 0.012 plus, that number is almost 0, e to the power, e to the power what? Negative 60,000? That should be a 0. I have a feeling that's a millisecond, because that number is huge there.
Was this like on the homework?
No, I just made that problem there, you know? Because that number, e to the negative.
Well, if it's on the paper, does it say 3 milliseconds or just 3
Oh.
seconds? Because sometimes, like, I remember one of the homeworks said 1 nanosecond.
12 milliamp. Well, I don't, I'm looking quickly because they just don't show all the steps there. Oh, I don't see that. I think it's 3 steps, but you know what? What's the equation here? When I write this equation here, I should say t minus 3. Because that doesn't kick in till t equals 3 seconds, right?
Mm-hmm.
T minus 3. Because it doesn't kick in, I keep forgetting about starting at 3, not at 0 here.
Yeah,
T minus 3, t minus 3. So this will be
that would be 0.
0 here. E to the 0, which is what? That's a 1, right? So 0.012 plus k is equal to 0. K equals negative 0.012. Now, once we know what k is, we know the current as a function of time is going to be, I can convert that to milli, 12 minus 12 e to the power of negative 20,000 t minus 3 milliamp for t greater than 0.
So that would be the equation.
Yep. 12 minus 12 e to the power.
Now, why'd you make it 12? Because you made it
Milli.
Milli.
Yeah, I just don't want to use 0.1012.
Yeah.
I could have used that, but I said 12 milli. Yeah. Yeah, don't forget this actually didn't kick in till t equals, I kept forgetting that's a 3, not a 0. If it was 0, that would be 0, 0, and that would be a 0. But this one will be t, not t minus 0. But because you kick in at t equals 3 seconds, we have to adjust for that. 3, 3, 3, 3. And that says the equation for that only good for t greater than 3. When equal to 3, that's equivalent to 0. That's the switch. When the switch goes up, 3 minus 3 is 0. That's the 0 time there. So anytime that number is different than 0, we have to subtract that number. You don't see a lot of these where 3, 2, it's always 0. So that's why it's a habit. I didn't even think of the 3 until like, oh, I forgot to write a 3 here. I forgot to write a 3 here. I forgot to write a 3 here. Yes. Oh, 3. Yep, greater than 3 again. Told you. This is for time greater than 3. There's nothing below 0. Notice nothing below that. There's no current, 0. So only at 3 seconds when it kicks in. So if you look at the graph, this is the 3 second. The current was really 0 up to here. So what's going to happen after that? What will happen to that equation when this is 3? E to the 0, which is what? 1? What's 12 minus 12? 0. What happens? So it'll be right here. What happens when it's 4 seconds? 4 minus 3? Well, 4 is too big. Let's say, I don't know, because that's 2,000. Well, let's leave it 4. Let's leave it 4. What happened when this is 4 seconds? What's 4 minus 3? 1? E to the minus 20. What's e to the minus 20? 0, right? 0 times 12, so this actually goes like this. 12. It's going to charge. So 0 till it hits 3 seconds, then it's going to go like this.